Hello everyone, thanks for liking, commenting, sharing, subscribing, referring these videos. In this video, we will talk about molecular orbital configuration of few basic cases like hydrogen. So hydrogen, as we know, it is, if you talk about H2 molecule, okay, so what will be the configuration? It is sigma 1s2. And if it is, let's say, helium 2, we write sigma 1s2, sigma 1s star 2. So what is star representing here? It represents anti-bonding, right? It represents anti-bonding. And what does sigma 1s represent? It represents bonding molecular orbital, or BMO. This is called anti-bonding molecular orbital, or ABMO. So before we go into the details of critical things and other details, let's talk about a very simple term called bond order, which is defined as half of bonding members electron minus anti-bonding electrons. So if you apply this logic, how many bonding electrons are there? 2 bonding electrons and no anti-bonding electrons. So answer is half of 2 minus 0, which is 1. Hence hydrogen is showing a single bond order. Let's try the same thing for this bond order. So half of bonding molecular orbitals, we have 2 electron, and anti-bonding is also carrying 2. So this is 2 minus 2, which will be 0. Hence bond order is 0. If bond order is 0 means no bond exists basically. Okay, no bond exists, and we can say that helium is, that's why what you call inert form, or it is just in the form of He atom. It is not forming any He2. Okay, that's one part. So the next question is, what is the sigma 1s and what is sigma 1s star? For those who don't know this, I'll just revise it quickly. So what happens if we talk about hydrogen and hydrogen, they carry 1s orbital. 1s orbital is 1s1 for both. And when we talk about molecular orbital, we are talking about overlapping of these atomic orbitals. So when you overlap these orbitals, we create corresponding molecular orbitals of same number. Okay. So overlapping can be constructive to give sigma 1s, can be destructive to give sigma 1s star. If it is constructive, it gives sigma 1s. If it is destructive, it gives sigma 1s star. So what is the result here? These two electrons which are drawn here, they will be marked. First filling will start from minimum energy level, and as we know, in this minimum energy level is here 1 2. So your answer for this question will become, for the given energy considerations, it becomes sigma 1s will carry both the electrons and sigma 1s star will remain empty without anything. So let me just repeat once again. This is atomic orbitals you are taking. You are overlapping them to form molecular orbitals, which I have written here. This is BMO, bonding molecular orbital, and this is ABMO, anti-bonding molecular orbital. To maintain the energy level balance, you are keeping the gap between this, how below it is, same height above this would be, so that energy is conserved. We can't create or destroy energy in such cases, right? I hope this example is now very clear. And helium 2 also we can draw in similar way. In helium 2, this sigma 1s star will also be considered. Let's proceed further. After sigma 1s and sigma 1s star, the next thing is sigma 2pz. Okay, so first you say sigma 1s and sigma 1s star, then you say sigma 2s and sigma 2s star. So let's write that also. Let's complete that also. And after that we reach out to sigma 2pz, pi 2px, pi 2py, or it could be pi 2px, pi 2py, and then sigma 2pz. So remember, this is same in both the situations. Only thing is, while writing configuration, you have to be careful whether it is sigma 2pz, pi 2px, pi 2py, or this. So remember, this is applicable for the cases B2, C2, N2. Right? So for this, I'll record a separate video why it is happening and all those things. Currently, our aim is to write electronic configuration. So let's say somebody asks me, write down the configuration for oxygen, O2. So we'll say O2 is not lying in the second one, it is lying in the first one. So we should know what will happen after this. It is pi star 2px, pi star 2py, sigma star 2pz. Hence, same thing you can copy here also. So let's say we are talking about oxygen. So I'll just take this detail, this one, and I will try to explain you oxygen configuration with the help of this. So O2 is basically 8 plus 8, 16. For 16 members, 2, 2, 4, 2, 6, 2, 8, 2, 10. Now after 10, 11, 12, 13, and 14. Why I am doing this? I am not violating Hund's multiplicity. So 1, 1, plus 1, plus 1. That is the right approach. And then, so how many we have counted up to this? 10, and these are 4. So 10, 4, 14. Now remaining is 2. So 1 goes here and 1 comes here. That's all. And what about this last part, sigma 2pz, that remains vacant, 0 here. So ultimately, if you observe, this is pi star 2px, pi star 2py, which indicates that this particular thing, pi star 2px, pi star 2py, is showing paramagnetic behavior because of unpaired electron in this particular orbital. So if somebody asks what is bond order of this thing, you start counting. Bonding is 2, 2, 4, 2, 6, 4, 10. Okay, there are 10 in numbers. And how many anti-bondings? Let's count. 2 plus 2 plus 1 plus 1. That is 6 in numbers. So answer is 2. Okay, and the trick could be why to count this and this, because they are anyway cancelling out each other. We can count the last one only. So I hope you learned about oxygen's paramagneticity, you learned about oxygen's bond order, you learned about oxygen's electronic configuration, you learned about B2C2N2 configuration changes, and you also learned about helium and lithium and hydrogen cases. And you also learned what is the meaning of this BMO and ABMO. Thank you very much for watching this video. Keep liking, subscribing, sharing and commenting. Thank you very much.